We are Team 54, and this is our proposal for our GEARS, or Global Emergency Autonomous Response System. Our robot goes by the same name, GEARS, or Geraldine Elliott Alexander Rosalita Salvador the 54th. The broad purpose of the GEARS is to deliver life-saving supplies in emergency situations. There are many guidelines that the robot needed to meet. The overall goal of the robot is to navigate through damaged areas in order to transport cargo to populations in need. Part of this requirement is hazard avoidance and characterization. This means the GEARS must be able to autonomously remain a safe distance from hazards it may encounter, such as cesium-137, which is represented by an infrared emitting device, and MRI, which is represented by a magnet. The GEARS must stay a minimum radius of 4 inches from the infrared and 5 inches from the magnet for the journey to be considered successful. The robot must also transmit a map of its surroundings, which includes the path it traverses and any hazards it encounters along the way. The next requirement is the communication of the cargo contents through universal symbols. Whether the cargo is transporting supplies of food and water, emergency shelter, medication, or fuel, there must be a symbol that would be recognized by all cultures to signify what the cargo contains. This must also be done in a manner that wouldn't be deemed hostile, whether that be the way that the robot interacts or how it looks. There are multiple deliverables that go hand in hand with this proposal. The first is the design notebook. This is a constantly updated document that is used to guide meetings and display developments, research, and pictures or diagrams related to the project. The second is the DSR, or Design Specification Review. This is where all the preliminary plans and ideas for the project are presented through means such as Gantt charts, work breakdown structures, and other such tools. Finally, of course, there is the demonstration of the GEARS in action, the presentation based on our findings, and a final report to show everything that was learned throughout the process.
Hi, I'm Amelia Markert, and I'll be discussing the team's project management. The first thing we did as a team was determine how we would conduct meetings. We decided to have specific goals going into each meeting and having tasks assigned to group members to accomplish before the next meeting. We made sure to never go more than a week without meeting, and meetings increased in density as the demonstration neared. To help us identify specific goals we wanted the GEARS to achieve, as well as key factors of the design process, we created a needs finding chart. This allowed us to analyze what the client wanted, convert that into technical need of the robot, and then create a goal for its final prototype and performance. Next, we created a functional block diagram in order to determine the main inputs and outputs of the system. This really allowed us to see what was expected of the GEARS and begin to look at ways these functions would connect with each other. After that, we created the work breakdown structure. This allowed us to really plan our approach to this project as a whole. We included sections for planning, programming, designing and building, testing, and documenting our work. This gave us a solid structure to follow as we created the system. Lastly, we also included a Gantt chart. This involved elements of the work breakdown structure, but it really allowed us to give out individual responsibility and ensure that this experience was a group effort.
Hi, my name is Eleanor Dias, and I'll be talking about the mechanics design philosophy of our GEARS iteration. Out of one of our first meetings, we developed this morphological chart, which shows the 7 most important functions derived from our functional block diagram, and 2 to 3 ideas for how we would accomplish those functions. One of the most important functions for the robot was the driving method. Although we initially considered a 2-wheel drive method because it was easier to implement and it had fewer materials, we ultimately decided on a 4-wheel drive method because although there were more materials and weight, this method is stronger on uncertain terrain, which we know it would be on during a disaster scenario, and crucially it enables a smaller turning radius, which allows the robot to navigate in small spaces and reverse out of a small area of the maze. When selecting our magnetic sensor, we initially thought of a Hall sensor because it is easier to attach to the robot due to its 3D printed case, and it detects the magnetic presence well, but decided on the IMU because although it needs calibration, it is able to detect magnetic force, magnitude, and direction, and it is able to track the location of the robot, which is crucial for our hazard mapping. And then with our infrared sensor, although we might have considered a color sensor initially to detect the change in the surroundings, due to the nature of the IR beacons, we decided on the IR sensor, which measures the intensity in watts per meter squared of the infrared radiation present and is able to detect from a longer range. Our drop-off device, which we developed, but unfortunately due to a miscommunication with the teaching team, did not attach to our final iteration. It was a claw, and as the robot reached the end of the maze, the claw would open and the cargo would be deposited gently on the ground. Here's our cargo container that we developed for that purpose. It is a box with a lid that rotates around a pin. The pin drops down from the lid, as you can see in the 3D rendering on the top right, and it goes into the base, as you can see in the bottom right 3D rendering. And then our 3D printed final cargo box is seen on the left, in a closed position on the top, and then in an open position on the bottom. So you can see how the lid is able to rotate around that one point, and the cargo, which we developed to have specifically the volume in the requirements, is able to be inserted and then removed when necessary. This enables secure transport and opens easily for anyone who may encounter it. One of our unique features of our robot was a sport mode. As you can see on the top photo, the blue Technic pins attached to the yellow pie case are in a horizontal position, which is nice, but because it shifts all the weight towards the center of the robot, which keeps the center of gravity there and enables a smaller turning radius. But when we needed to maintain the robot and access those sensor ports, we were able to put those Technic pins into a vertical position, and that enabled access to the battery and those sensor ports. Lastly, our sensor positions. We mounted the ultrasonic sensor and the IR sensor above the cargo so they could have the best vantage point for detecting both the walls and the IR beacons, but we decided to mount the IMU lower and down in front of the robot so that it would be able to see the magnetic beacons without having to detect through any other parts of our robot.
Now I will talk about the software of our project, which is essentially how quantitative information guided gears. To start with the basics, the code begins by defining the motor ports and other sensor ports with defined constants, which allows for the easiest method of changing ports. As far as movement, the two essential parts of it are the actual movement of the motors and the amount of time that it runs for. The set motor DPS function, which takes the port and speed as parameters, is used to set the running speed of the motors. We deemed that using degrees per second would be the most precise way to define the speed and would allow for an easy calculation of distance traveled. Time.sleep is used to define how long the motors will run before the while loop repeats. Time.sleep essentially tells the code to stop moving forward, allowing for other movements and calculations in the code to take place. For the following 3 slides, we performed analyses on the sensors to determine the model that best fits the data, which is where the numbers I will mention come from. The second most important part of the code is the obstacle detection code. An ultrasonic sensor is used for this. This code works by reading in the distance from the sensor every 10 milliseconds and performing actions based on what it sees. If the distance is above 40 centimeters, the robot continues moving forward at its normal speed. If the object is between 15 to 40 centimeters away, gears slows down to 70% of the normal speed. And lastly, if it is less than 15 centimeters away, gears turns right 90 degrees and takes in another reading. If it sees another wall, it turns left 180 degrees. If it sees another wall, it turns 90 degrees to the left, thus effectively turning around and moving backwards. This obstacle detection code is based around the idea that, with simple mazes, continuously turning right will eventually get you out of the maze. Research was performed on different strategies, and this one seemed to be the easiest and simplest way to integrate pathfinding logic. Next comes hazard detection. For magnet detection, we use the IMU sensor, which measures magnetic fields. After reading in this information, the code splits it up into X, Y, and Z values. The magnitude of the reading is calculated by taking the square of the sum of each of the components squared. If the magnitude is greater than 160, the code returns true, saying that a magnet was detected. Once a magnet is detected, it is avoided in the same way that walls are avoided, by turning right 90 degrees, then left 180 degrees, or left 90 degrees if needed. The number for 160 comes from the various testing we did with the magnetic beacons. A linear model was achieved when plotting the magnetic field versus the distance by taking the natural log of both axes. Next is the IR detection. We use the dual intensity sensor for this portion of the code. The IR intensity was read into the variables sensor1_value and sensor2_value. We took the average of these readings, as it is most likely that the sensor will only sense the IR beacon when it is directly in front of gears due to the shape of the sensor. Then, if the average is above 80 or if the reading of either of the sensors is above 30, the IR beacon is around 4 to 5 inches in front of the robot. Just as was done with the magnet, the IR beacon will be avoided as if it were a wall. The relationship between the IR intensity and distance was determined to be linear when the natural log of intensity was plotted against the distance. The turning mechanism for this robot was created so that the parameters are speed, degrees to turn, and direction, making it extremely reusable. First of all, it stops the motors to prepare for the turn. Then, it calculates the degrees to turn based on the circumference of the robot and of the wheels. From that, it calculates the total turn time by dividing the degrees by the speed. Then, depending on the direction the robot wants to turn, it sets 1 to the positive speed and 1 to the negative speed. Finally, the program sleeps for the calculated turn time, ensuring the turn is completed before the code moves on. The next section I'm going to talk about is the mapping portion of this project. For mapping location, we used a large NumPy array consisting of zeros. The starting location of the robot was set to be the exact middle of this array. The location of the robot is determined by the direction it faces, which will subsequently update the current column and current row of the robot. For example, if the robot moves forward but is facing the right direction, the current column number will increase by 1 while the current row number stays the same. The location of the robot was plotted every 10 centimeters, ensuring the robot would plot all of its turn. After completion, the array is stripped of any excess columns or rows of zeros. Then, the map is printed to the external file element by element as shown in the bottom right image. Hazards were mapped as soon as they were spotted and used a similar technique as described before. The location of the hazards was determined by the X, Y, and Z magnitudes for the IMU sensor and the difference in the sensor 1 and sensor 2 values for the IR sensor. For example, if the right sensor on the IR sensor had a much greater reading than the left, it was determined that the beacon was likely to the right of the robot. When it comes to outputting the hazard map, the array is searched for values of 2 or 3 depending on the reading. From there, it outputs the coordinates found and a description of the obstacle that was sensed.
As with every system, there were some things that went incredibly well and a few things that still need improvement. I'll begin with a few of the things that the gears did that exceeded expectations. For the movement of the gears, we implemented a gear train which positively impacted the robot's performance in multiple ways. First, it allowed for the robot to have four-wheel drive while only using 2 motors, one for the left side and one for the right. This worked by having a motor on the front end of the robot that rotated the front wheel and using gears with a 1-to-1 ratio leading to the back wheel that rotated the back in unison with the front. This also enabled the robot to turn on a dime, which was especially beneficial for any tight corners that it may need to encounter when deployed. This also helps keep the robot compact as the gear train doesn't add much bulk, especially in comparison to another 2 motors. The mapping system was another positive feature of the gears. Once the code began to run, it started to put together a map of everywhere the robot had been. With that, it also had special markers for the starting and ending points of the maze. It also mapped the locations of any hazards it came across by detecting a change in the direction and magnitude of Teslas for the magnet and intensity for the IR beacon. Once the map was finalized, it also cut out any unneeded rows or columns to make for a more concise and useful map. The cargo holder was 3D printed to hold any cargo that the gears may need to hold. It was a cube that could be opened either by simply rotating the lid or by lifting the lid off the base. There were arrows on the top of the lid indicating that twisting was an option to open the cargo, but with the ability to also be opened through lifting, it was easily accessible no matter who might encounter it. The inside was also the perfect size to carry the cargo without having too much extra space that would have just bulked up the gears.
Now we will discuss the negative aspects of our system. One issue the gears ran into during the demonstration was turning the correct amount of degrees in the maze. During the first few trials, turns were under 90 degrees, causing the robot to almost run into walls. This issue was likely due to calculation errors with the circumference of the gears, as that is a major factor in the turning, or it could have been caused by the changing ground material, as tests were done on tile and carpet did have 90-degree turns, but the floor of the demonstration maps were made out of a paper material. This issue was corrected as the demonstration continued, and the robot was able to turn at the correct angle for the remainder of the time. Another issue with the turning was the fact that our gears only had one ultrasonic sensor. It was believed that this would be fine during the demonstration, but it was realized that there was an error in logic because that meant the robot would not be able to turn if there was not a wall directly in front of it. This meant it would often get stuck as there were walls in the center of the maze that were not attached to other walls, and the gears had a hard time finding the exit. Another issue the robot had during the demonstration was that the gears began turning early when the wall was supposed to be outside of the range of the ultrasonic. The test code was run to discover what the issue was and was found to not be an issue with the ultrasonic sensors as originally thought, but as an issue with the IMU sensor. It was discovered that the IMU was picking up magnetic data from the metal being used to hold up the maze walls. To combat this issue, one would need to increase detection strength of the IMU in the future, but this would cause problems with the accuracy of mapping magnetic beacons as another requirement of the gears. Towards the beginning of this project, there was a cargo drop-off method in the form of a claw that would expand to allow the cargo to drop off the gears, but due to a miscommunication from the teaching team, it was determined that this mechanism was not necessary and was not attached in our final iteration. Having this mechanism would have caused problems in the new structure of the gears, which would have needed a complete reconstruction, as well as constants in the code that needed to be reevaluated. Because of this, the robot was unable to drop off the cargo in the final demonstration. In the future, the mechanism would need to be reintegrated into the hardware and software of the gears to be successful in delivering the cargo.
Overall, the gears performed well in the completion of its tasks. In terms of navigation, it successfully made its way out of the maze and avoided all hazards. With that, it was able to correctly map its path with all the additional functions, such as the entrance, exit, and hazard locations. There were two areas where the robot encountered slight difficulties. First, at a certain point in the maze, the robot was detecting one of the metal holders for the walls as a magnet, which was causing the gears to turn the wrong direction. To solve this issue, the magnitude of charge that the code used to qualify a charge as a magnetic hazard had been raised. Second, the gears did not have a functioning cargo drop-off mechanism due to the conflicting instructions given. By the time the instructions had been altered, there was not a viable manner to remove the cargo from the finalized robot. The cargo drop-off technique that we would have implemented was a claw mechanism using the rotating motor. This claw would hold the cargo throughout the journey and then drop it to the ground upon exiting the maze. Another area for improvement that was implemented during the demonstration was the turning angle of the gears. All prior testing for the robot had been done on carpet, and when turns were implemented on that type of flooring, it turned in increments of exactly 90 degrees. However, upon entering the demo maze and being on paper, the turning was slightly off. This required a slight adjustment of the code to tell the robot to turn 100 degrees. Of course, the robot only physically rotated 90 degrees, but based on what the code was relaying to the gears, 90 degrees on paper translated to 100 in the code. Despite these minor setbacks, the gears completed a satisfactory mission that qualifies it as an excellent prototype for the task at hand.